Okay, so hello everybody. We are back with our webinars uh, provided by the Solid State Circuits and Electronic Device Society South Brazil chapter. Here we are honored to have Farhana Sheikh from Intel as a distinguished talk presenter. She will talk about circuit and systems for 2.5D, 3D heterogeneous integration of chiplets and FPGAs. Dr. Farhana seeks next generation wireless and sensing applications. She has published over 50 papers and 22 patents and initiated the AIB 3D open source specification for 2D chiplet heterogeneous integration. I would like to point out that outside of Intel, she's a volunteer at the IEEE Solid State Circuit Society and the Solid State's Women in Circuits Committee Chair. She's a co-recipient of 2020, 2019, 2012 ISCC Outstanding Paper Awards. In 2021, Farhana has recognized for her mentorship for work with students and faculty by the Semiconductor Research Corporation that awarded her the 2011 Mahbub Khan Outstanding Industry Liaison Award. Recently, she was elected ISCC Member at Large for 2022 and 2024. It's really a pleasure to have you here. So welcome. The floor is yours.
Thank you very much. It's an honor to speak to all the folks here. And thank you for the very kind invitation. So I'm very happy to be here and happy to talk about some of the work that I'm involved in at Intel. I'd like to also acknowledge my collaborators that are listed over here. So this is just a short disclaimer from Intel, which I'm required to put into all my external talks. So I'll just flash it for now. And so here's my motivation. So as you know, there is now a convergence of intelligence, compute, and communications. And so in the next decade, we're going to see a lot of this happening. And there's been a lot of studies, and I've included references at the end of this presentation. But a number of studies are saying that we'll reach up to 500 billion connected devices by 2030. This is really a very large number, 59 times larger than the expected world population. And then we'll also be looking at very high usage of communications and compute for new and emergent applications such as AR, VR, augmented reality, virtual reality, machine-to-machine connectivity, imaging, and sensing. And so what we foresee is really that instead of humans becoming the dominant users of next-generation communication and compute systems, it's going to be objects. So, we're going to see a lot of heavy use of our spectrum, heavy use of our communication technology, and requirement of a very high performance compute across the entire infrastructure that we have from the cloud to the edge. What we're going to need is really some intelligence at the edge to improve the performance and optimize the network, and also to have power reduction and energy efficiency for all the circuits that we design into these systems. We'll also want some intelligence in terms of wideband spectrum sensing, and that's because there'll be so much data coming in and so much interference that we will need the intelligence to figure out, if there's any malicious attack and be able to detect that right in real time and at the edge. So you can see here that there's a graph of, what, 6G might look like with respect to 5G. So you can see over here that, there'll be significant improvement in connectivity density, energy efficiency is required, spectral efficiency, and the data rate is really on terabits per second over here. And what we're predicting is that, from your personal devices through to your mobile devices and through the base station and the core and the cloud, what we need actually some kind of fusion between the communication systems and the compute systems. And of course, we all want more and more compute because, I want to be able to stream, high definition video to my mobile devices, but that's going to require a very high performance link to my base station. And then the offload of the processing I want to do on a very high performance core. And then whatever I can do in the cloud, I want to be able to run that efficiently on my server systems. So in this talk, I'm going to talk about, where we are with respect to FPGAs and Moore's law. So, what was predicted in Moore's law and how FPGAs have been sort of down that path, maybe probably the first compute platforms that have really been embracing what was predicted in Moore's law. And then, microprocessors have been following that. And we see that currently with a lot of, the multi-die systems that are coming out in terms of microprocessor architectures. But I'm going to focus on FPGAs, and we're going to talk about, how this came about, we'll look a little bit about the history of where FPGAs came from and how we got to a point where we actually embrace heterogeneity and we want customized flexibility. Then we'll see how we're leveraging some of the newer integration technologies, such as EMIB and interposer integration for FPGAs. And then I'll show a few examples, current examples of how we have leveraged these up and coming technologies that I call sort of, they sort of are bucketed in sort of the new wave in scaling. And then near the end of the talk, we'll see how we can leverage some of the advanced micro 3D and micro and nano 3D technologies for new systems that will require such technologies. And we'll see how 6G is really one of the primary drivers of the use of these technologies, because without these technologies, it'll be very hard to implement 6G systems. And then I'm going to conclude with introducing an early version of the open standard that can allow third parties to integrate into your 3D system using a standard interface. And this is an open source standard that Intel has been sort of driving. And I was in the very early phases, and we do want this to be adopted as part of the UCIe consortium. So we will want your opinions and your feedback on this. It's right now in version 0.5 phase, but I'll show you where we are with that. So let's go back in history, and everybody knows about the famous article from Gordon Moore in 1965, where he really articulated very well that it is going to be more economical to build large systems out of smaller functions, which is highlighted here, and then which are separately packaged and interconnected, right? So we've been doing this for a very long time. I mean, it's heterogeneous integration is not new. It has been around, and you can see this in the very in the cell phones in the past, where they've been the primary users of heterogeneous integration. But really we're in a phase now where we actually depend on this highly for yield and for enhancing our functionality. So what I call is the future is really going towards how do we get more functional density into our circuits and systems. And the system is now really becoming the package where we're stuffing a lot of transistors and different types of technologies into a single multi-chip package. We'll talk about this a little bit more, but I highlighted, how we've integrated optical into with an FPGA, and we'll talk a little bit about this in detail as we go through the presentation. And then we'll also talk about, wireless systems and how FPGAs can help in that respect as well. And interestingly enough, for more, he even mentioned phased array systems and how we would start integrating these to get the best bang for the buck. And you can see that we have even gotten to that point where at ISSC 2019, it's a project that I worked on where we integrated the antennas and the circuits on a package. Now, let's focus on flexibility for now, because it was mentioned here, is that, flexibility is really something that we do want from our systems, and FPGAs are, they embody flexibility, and this, march towards FPGA and flexible systems came very early on with, the work that was done by Berkeley, and it was published in the VLSI Signal Processing Workshop in 1996. And then further on in ISSC 2000, Berkeley also worked with ST Micro, and they published FPGA system that was kind of like a SoC FPGA system where they had an ARM 8 core and an FPGA. So you can see that everything here is monolithically integrated, but it is heterogeneous in the sense that it is very different types of compute all integrated into one chip. Now, if we look at where we're heading towards towards the future and what the market is going to be worth, really embedded FPGAs have been seen as more of a niche market, and it's touted as being only worth about a $4 billion market. However, if you attach updatable hardware and application-specific accelerators that is in sort of a heterogeneous compute environment in the data center, then this will really grow your market. And so this is really important for companies like AMD and Intel, where they do see this need where FPGAs can enhance their data center processing, and you already know that server systems can really leverage FPGAs to customize the server compute. And so there is a reason why Intel bought Altera, and there is a reason why AMD bought Xilinx. But what we're going to focus on here is really the FPGA and how we can enhance the FPGA so that we can actually grow the market for the FPGA. Now, how do we do that? One way to do that is to leverage modularity, again, like it was mentioned in Moore's Law. And what are the different circuits and systems and packaging technologies that we need to do that? We have some examples here where in 2011 and 2008, Intel published their EMIB technology, which is a die-to-die interface technology that's a packaging technology. So you have basically thousands of very parallel wires that are embedded into the package, and you can actually send data from one die to another die through these multiple wires that are embedded into the package. In 2014, Xilinx also figured out that they could use something called stacked silicon interconnect and die stacking to enhance their FPGA systems by integrating data converters. So you can see that there's a bunch of DACs here and a bunch of ADCs here. They actually create this new circuit technology, which is called stacked silicon interconnect, and they integrate that with their Vertex FPGA. So where does communication and FPGAs come in? Well, we can see already that, the academics have been working on this for some time, 2016, where they're looking at, multi-die heterogeneous integration by, trying to figure out how they can bring the antenna closer to the circuit and the RF system. So they've done this through, either PCB or interposer, and, even using some quartz dielectric to couple that with their systems. So, and then Intel has been looking at, doing this directly antenna integration on package. This is a 75 gigahertz system that they built with this, 64 element array. And then Berkeley has been figured out that, okay, yeah, we need to put everything much closer to where we're going to do the baseband processing, which is typically done in the FPGA as a virtual baseband or a soft baseband. And so what they did was, and it pretty crude, is that they put the FPGA board on this, wooden board, and then they added the ADCs with some interconnect. And so they put the ADCs closer to the FPGA. And so they got this interesting, prototype system where they actually got, the baseband plus the ADCs, and then they can add on the RF system to communicate with the analog, right? So really, you can see where things are headed, right? Is that we really would like to get all of this on a package. So not just the RF and the antenna, as we see here, but we want the ADCs, we want the baseband, we want the FPGA, we all want this all in one package, and we'll see how we can get there. So continuing with a little bit of history and evolution of where we got FPGAs plus chiplets. So I'll continue with a little bit more history here. So we started off, as I said, with SoC FPGA. And, this was done by both Xilinx and Altera. And you see that, you got the FPGA, you got the SRAM, you have DFT, you have a bunch of memory, and then you have interconnects. And so this really became what FPGAs used to be like in the past. But very soon after this, people realized that this is not going to give you a very large market as was predicted. So they figured out how, they wanted to find a way to actually enhance this, and they wanted to figure out how to incorporate, in other interfaces, so optical, SerDes. And so both Xilinx and Altera started integrating, SerDes and other interfaces to the FPGA so that they could actually communicate electrically with electrical links or wirelessly with the data converters, as you saw in the previous slide. Now, how do we do this efficiently, right? So as I mentioned, these systems, they require both RF, they require data converters, so analog mixed signal circuits, they require processing, compute, they may require electrical links, memories, CPUs. Some of the FPGA systems even have a RISC processor in there, and they obviously need power delivery. You may need some DSP depending on the application. Now, if we start digging a little bit deeper and start looking at the technologies that we use to build these circuits, and you and all your circuit designer friends will, and of course me, will know that I want the best technology for my digital, so it has to be the most advanced node if I can get it. But maybe the advanced node is not the best. The advanced digital node is probably not the best node to use for my optical I/O or even for my RF, right? I want a technology that is kind of tuned to delivering me the best RF performance. And we can see from this graph, it's not necessarily the same technology node that I use for my digital. For example, if I look at my logic and memory, which is my digital node, I want to optimize for leakage, density, and speed. And I don't really care about passives and high voltage operation, right? But if I look at my RF circuits, I would like to design my RF circuits on a technology that has great passives, that can deliver me great speed, and can deliver me some high voltage, performance. So very different from what a digital technology might require. And then for my IOs, same thing, right? I don't really care about too much about density, but I do care about high voltage operation. And for analog mixed signal, I actually want the whole thing. I want everything. So, really, very disparate technologies are required for different functions, right? So, as a circuit designer, I would want the most optimal technology for my function. How do we do this? Well, we do this basically using heterogeneous integration. So how about I decouple my technology roadmap for my RF and my wireline links from my digital technology that I'm going to use for my FPGA, for example. And then I use heterogeneous integration to put them together. So that's an idea. Now, this actually really happened in 2013, where, you say, well, necessity is the mother of invention here, is that, Intel bought Altera, and Intel wanted the FPGAs to start moving to, using Intel technology, 14 nanometer FinFET. But their wireline links, their SerDes, their serial links, were actually developed on TSMC, and they actually didn't have, so the transceivers, they were in TSMC 20 nanometer. They didn't have a lot of time to move the transceivers. It's much harder to move the transceivers over to a new technology node, especially in a technology that was optimized for digital. So, the transceiver guys didn't really want to move to Intel for their transceivers, but the FPGA, was going to get better performance out of Intel, the digitally optimized technology. So they said, well, Intel has something that they just released. It's like a Intel EMIB technology. So why don't we actually keep the transceivers on 20 nanometer and then move the FPGA to Intel 14? And that's exactly what happened. And that became the first use of EMIB, and then it basically started the whole FPGA chiplet, I would say revolution, where, out of basic necessity, we got to this point where we had these FPGA and chiplet architectures. And I'm going to dig a little bit deeper into that. So here's the first publication where they showed the FPGA die built on Intel 14 nanometer process. And they had the EMIB bridge, and they had AIB 1.0 integrated on the die and the chiplet. So they were able to put AIB on the transceiver tile, and then they were able to put AIB on the FPGA. And now you can see that there's 6 different chiplet slots where you can add a transceiver in each of these 6 chiplet slots. And so what we've done here is we've kind of easily enhanced the capability of the FPGA platform by integrating 6 transceivers with the FPGA, right? So you can now connect 6 different things up to the transceiver die, and then have that communicate with the FPGA. So this is kind of really cool, because what you've done here is you've actually decoupled the transceiver roadmap from the FPGA roadmap. And that's what you want to do, is you want the FPGA to do whatever it does. Maybe the FPGA stays on 14 nanometer for a very long time, because it doesn't need to change. But maybe you have a new idea or a new transceiver tile or a new data converter or a new machine learning tile that you want to integrate with the FPGA. And you can build that in any process that you want, as long as it has an AIB, PHY, and some kind of MAC layer protocol that will work over this EMIB bridge. So let's take a little bit closer look at the EMIB bridge. So this is an embedded bridge. And this is like what a standard package might look like in terms of bump pitch, density, and energy per bit. And this is the Intel Agilex FPGA that uses the EMIB bridge. So it has DDR memory, and then it has a bunch of transceiver tiles. So this is a 2.5D integration. And so the EMIB bridge has, so on a regular standard package, you'll see C4 bumps, so just like this, they're like big. But the EMIB bumps are much smaller. So here you can see the bump pitch, 100 microns here, but the bump pitch for EMIB is anywhere between 55 to 36. So you can see that you can connect a whole bunch more wires to these bumps, right? It's much denser. So your bump density definitely improves quite a bit. Your energy per bit also improves quite a bit at the raw level. A 3.4 times reduction in your IO energy per bit. So really very useful here. So instead of having, in a standard package where you're using a serial link, for example, or connecting up from one package part to another package part on a board, this is much more efficient. It actually will help reduce your power significantly in the IO and will actually help you get much higher bandwidth. Now, in order to leverage something like that, even if you don't use a package, EMIB package part, EMIB packaging technology, and you want to interconnect your dies on, passive interposer, for example, you still need a PHY interface. And you'd want to get an open source PHY interface because, for example, you may not want to build every single chiplet for yourself, and you may want someone else to help you build your platform. And so how do you do that? You actually will want to use a standard interface that everybody knows about. And so what Intel did through the DARPA CHIPS program and CHIPS Alliance was that they came up with an advanced interface bus specification. And this is open source, and you can pick it up at GitHub. And there is now version 2 available. So what this allows you to do is to build a PHY interface, which is a highly parallel interface where you have 2 gigabits per second per wire. And you can, if you're going to use EMIB, you can, it works with pretty much any bump density you want. The reason why we put bump density here is that we have a hard macro that you can get from Intel that is built for specific bump density, but there's nothing preventing you from building your own AIB for whatever application that you want. It really is independent or agnostic to the integration and packaging technology that you're using. Now, right now, what we're working on is AIB 2.0. The specification has been released. It's much higher bandwidth. It has much higher, bandwidth per millimeter at the shoreline, and then the energy per bit is also much reduced. It is also backward compatible to AIB 1.0. So we do encourage you to take a look at this. It allows, us to integrate anybody's chiplets that have this AIB interface with our FPGAs. Now, what is the real power of this open source die-to-die interface? So what I can say is that, we have been working with DARPA and different universities and different, industry collaborators on the DARPA CHIPS program for some time, which really has, pushed this to the forefront in terms of, I would say really pushing the chiplet a phenomenon to the forefront in terms of the entire industry. So one of the first implementations of the open source AIB 1.0 die-to-die interface was done by University of Michigan at Ann Arbor. And what they did was they built their own AIB interface. They knew that, Stratix 10 FPGA, the Intel FPGA had an AIB 1.0 interface as well. And so they wanted to connect up their chiplet to our FPGA. So that's actually done over here. And then they also wanted to use the same AIB to do connect up multiples of their chiplets on passive interposers. So you can see that the AIB standard, it's agnostic to the packaging technology, right? Or the integration technology. I would call it integration technology, where you can see that the AIB 1.0 works with interposer, and then it also works with the EMIB 55. So they were able to reuse their chiplets in different ways. So another, innovation here is that now I built one chiplet and I can use it in multiple different ways. I can put two together to get more performance. I can put it with an FPGA, and I can get like a configurable compute with my accelerator, and that enhances the capabilities of my platform, right? Everybody would love to have a configurable compute right next to a hardened accelerator, so that I can, try different things and program different things in conjunction with my accelerator. This is, if you open the lid of the package, this is what you see. So you'll see that this is the Michigan chiplet. It was a 4x4 chiplet sitting right here. And actually it was implemented not even in Intel technology, it was implemented in TSMC technology. And it was sitting right next to this big Stratix 10 here. And then this is basically a SerDes tile sitting right here. You can see that the benefits of doing this are quite clear. So they use a simple parallel I/O design versus a complex serial I/O design, something like SerDes, where the area is much smaller. You can see the bandwidth density is greater, the latency is much smaller, and their actual performance was better in terms of the application. So all in all, this was a plus in multiple ways. And you can see here that, this is really interesting, is that you can see the micro bumps are really like tiny here versus the C4. Now, how about I want to connect, my machine learning and AI accelerator, and I would want to do some real-time edge intelligence, or, edge learning. How do I do that, right? And I want to be able to leverage the FPGA for, any programmable tasks that I might want to have in my system. So again, through some DARPA programs, we collaborated with Michigan, and we created this multi-chip package where we had the FPGA with the AIB, and then we had Petra, which is their DSP AI accelerator, with the AIB interface. And then we put them together using our EMIB package. Now this accelerator does matrix multiplication, it does FIR filtering, it does convolution, so it does a lot of things. And the performance was pretty high, so really it could do way more than what an FPGA might be able to do. So 6.97 teraflops per watt, and it does both DSP and machine learning. So you could put it for radio type of applications, or for just pure machine learning type of applications. Again, it was using the Michigan version of the AIB implementation, and then using the 55 micron EMIB packaging technology that Intel was working on. So we developed the package. We had added the FPGA interface, and then added the chiplet over here, which was a 4x4 millimeter square chiplet. This really was the first configurable matrix accelerator designed as a chiplet for FPGA. And it actually contains a lot of compute density. You can see about 400 to 500 gigaflops per millimeter squared using half floats. So, very capable accelerator that's coupled with FPGA. So you can imagine what this entire platform might be able to do now that it has this accelerator that could, you could deploy in various applications. How about optical interconnects? As I mentioned at the beginning of the talk, we were going to do a deep dive on this one. So another DARPA program where we work with IR Labs is looking at how do we integrate optical chiplets and FPGAs. And the reason why we want to do this is that we do foresee a significant amount of compute that's happening on these high performance systems, but then the interfaces become the limiting factor. So optical is a really great way to increase your I/O capacity. And so if we can integrate, optical links with our compute platforms, as in this case, where we actually embedded an optical transceiver, and you know that an optical transceiver uses all sorts of different types of technologies. It requires all sorts of different types of technologies for the circuit implementation. And it's very hard to couple that or integrate it with CMOS. I mean, there's many research projects where people are trying to, monolithically integrate optical with CMOS. But what we decided was, hey, let the optical guys do their thing on their own technology, whatever makes sense for them. And then we'll create the, the packaging and the integration technologies to integrate that optical chip with an FPGA. And this is really one of the first of its kind that's being published. And so we have, you can see here in very minute detail is that the C4 bumps are here, and then the EMIBs are so tiny. You can see them here. And again, this was leveraging the same FPGA. So you can see there's the same FPGA in every single platform with the same AIB and the same EMIB, but very different chiplets are being integrated. And you can see with using very different technology processes. You can see that this optical chiplet was, built in this Global Foundry 45 nanometer technology that is really customized for optical communication or optical links. And this was integrated, directly with the FPGA using the bridge and AIB. Really, this supports, very new high-performance compute architectures. So you can imagine putting this next to a big, huge server system that's going to send out terabits of data, and you really need the optical link to carry that data forward to whatever other compute happens next. And so the small form factor that we have here in this 55 by 55 millimeter square package, it allows you to enable these new communicate and compute architectures for intelligence at the edge. So as we go through a couple of years after 2019, recently there has been more advances in the optical chiplet, so new versions, and then the idea to actually put 5 of them on the Stratix 10 to get huge amounts of I/O bandwidth, 8 terabits per second. And this could really help in terms of facilitating, RF to optical, where you have terahertz RF and you want, you know, all that data to go to somewhere for compute, this could really facilitate that. It could facilitate high frequency radar systems. And, you know, this is just showing you how it was built, and then showing the AIB, the crossbar, and then the transceiver, and then how it actually goes to the, connects up to the outside world. And so you can see the packaged part right here. And then if you open the lid, you'll see that there's an FPGA and then the 5 tiles. I do recommend going to these papers if you want to learn more about these things. So what about wireless? You know, people have been trying to do this for a while. And, you know, for sub-6 gigahertz systems, you know, incorporating the FPGA with the antenna, you get this huge thing. But then as you move to millimeter wave frequencies, you can put everything on this little, you know, packaged part over here. And then, you know, if you want to array these out, so if you want to use custom off-the-shelf components, you know, build a test bed like what Berkeley folks did. And then, you know, DARPA has been looking at also monolithic integration in 3D, and, you know, this is how they might build their parts. So I want to focus on this one and, you know, show you how we took this idea from Berkeley and we actually figured out how to do this in a much smaller form factor. You can see how big this is. So this was actually shown at Hot Chips this year, where we took data converter chiplets from Texas Instruments, and these are data converters designed for 5G. So they have 16 element receive and transmit, and then they have a pretty wide bandwidth, you know, digital to analog converter, and then they have a pretty good analog to digital converter as well on there, which supports quite high bandwidth, 7 gigahertz. So what we did with, in conjunction, in collaboration with Texas Instruments, was that we put their analog front-end chiplet that it contains all of these ADC DACs, and we integrated on the FPGA. And then we also had a SerDes, so we could link up multiple of these systems together using the SerDes. And this is showing a little bit more detail of, you know, the Texas Instruments part. It was not built in Intel technology, it was built in another technology, and it was integrated with the Stratix 10. And then you see the SerDes here. And then on the board, what we did was we put, you know, the antennas and we put the remainder of the analog front end so that we could actually demonstrate a live receive and transmit system, right? And so you can see that, you know, it's very different in terms, you know, like look at this versus what Berkeley had to do for this very, you know, this large 64 element array. And so, you know, you can see this is a pretty nice system. And you can see the benefits of doing it this way, right? You can, the power, 25 watts versus half a watt, latency, 6 clock cycles, and the board complexity was much lower, right? So all in all, this is really paving the path forward for leveraging multi-die heterogeneous integration for wireless. So what I want to, you know, start, you know, closing up my talk with is that what do we do about next generation sub-terahertz wireless systems, which is 6G? And I want to sort of go through some of the, you know, big issues that we see with these systems if we are going to build them the sort of the traditional way. So traditionally, if we just look at the transmit path over here, you have, you know, a DSP that may contain some machine learning because we want some intelligence there. As per the standard, we want it to operate at a pretty high frequency because there's going to a lot of compute is needed here. And then, you know, you want to have some kind of reasonable amount of bandwidth per channel. And traditionally, the DSP and the analog, the mixed signal, and the RF front end are decoupled from each other. They're on different dies, and then they're connected up. So if we just look at the amount of channels that we'll have in a MIMO system, and then the amount of data that's going here, we're at 2 gigahertz per channel, going into the data converter, into the baseband, and then into the RF. We also need to send these analog signals at very high frequency to the RF front end, and that RF front end, the reason why it might be coupled is because at these high frequencies, you can't really build the PA or the LNA out of CMOS. You might want to go to a 3.5 device, such as GaN or indium phosphide. So if we start, calculating, so 4 to 6 bits over here, and then 8 to 10 bits coming out for imaging, and then we have all these very high frequency signals going into the front end, you can imagine what the I/O looks like here and what type of power is required. So we actually did a quick paper calculation, and we referenced this paper in GSSE 2022. If we were to look at a short reach link just for the digital to the analog, such as 112 gigabits per second serial link, for a 16 element, 16 user system, we would actually spend 5.7 watts just in this I/O, just here. So, and then if we wanted to move to higher frequencies, and this is a very small system for 6G, you want like 128 users, for example. This is going to go even higher, right? This is going to explode. So we have a problem in doing 6G wireless system and circuit design the traditional way. So how can I do that, right? So I have shown you, the standard package, the EMIB package, and then we also have 3D heterogeneous integration technologies such as Foveros, and then there's other technologies that are coming online. And we see this in this scaling graph where it all goes all the way from macro 3D, such as Foveros, to nano 3D, where you're doing monolithic 3D integration of devices where you're putting, say, again, NMOS device with a CMOS, PMOS device, right? So that's kind of a hybrid integration at the very nano level. Now, this is still very much research, but as we move from Foveros to hybrid bonding, where the bump pitch becomes very small, like less than 10 microns, we actually see, growing commercial availability of all these technologies. So is there a way to leverage these technologies for 6G? A little bit more detail. I'm not going to spend too much time on here, but I do recommend you go into looking at the references. But again, this was the nano 3D that I'm talking about, where we have the GaN with the CMOS. Again, I want you to go to the reference to look at this, since we are starting to encroach on the last 10 minutes of my talk. What I want to show you is that for 6G, we have an opportunity to use these 3D heterogeneous integration technologies in very innovative ways. So you could think about, the digital integrating with the analog front end using some kind of macro 3D or micro 3D integration, such as hybrid bonding or Foveros. You may also want to fuse the RFIC with the analog front, the analog baseband, and have the GaN with the CMOS connected up through some kind of hybrid bonding architecture, or even a nano 3D type of design. And then you may want to, like we did with our 75 or 70 gigahertz part, we integrated the antennas on the package. So you can see that this becomes like kind of like a radio cube, and it's a very small form factor. So as a circuit designer, we're used to dealing with just the tiny little nitty gritty, circuits that we want to build for each of these parts, but we can't really do that anymore. We have to start thinking about how we're going to put everything together. You can't really now design the RFIC and the ADC DAC and the digital separately. You have to think about how they might integrate with each other, and you have to think about the interfaces and making sure that, once you put all of these pieces together, that they're going to connect up correctly. So just, FYI, being a circuit designer, you may want to start thinking about how you may become a systems and circuit designer. Now, there's a lot of pluses in doing it this way. We get, integration density, we improve our yield, we are using the optimal design and technology for the components, we're improving our power performance and area, but we are getting a negative hit on the thermals, the power density, the interference, the noise. And then we're still not sure about, okay, what kind of, network on chip might be required, what kind of inter-die IO is required, and then how do we do power delivery to all of this? Do we need some kind of 3D power grid? So these are all open questions, and these I, highly recommend, if you're interested in this, there's a lot of research left to do in this area, so definitely, you can think about, your next research project. Where does the FPGA come into this? Well, the FPGA is always used now for a lot of the, the back-end baseband processing, and it's usually a soft baseband. It's not something that is hardened, it's configurable. And so we do need to somehow connect up the FPGA with the radio, and we, you could think about doing it using EMIB, as we've shown in the past. Now, I want to just quickly, get you to really understand the problem with the I/O, right? So here's an example of a digital beamformer, a system where we have the RF, the DACs, the ADCs, and then we have an adaptive digital beamforming chiplet with this little bit of memory. Now, if we look at just the I/O again here, right? The RF, the I/O between the digital and the RF, as I showed you before, in our earlier calculation was like 5.7 watts. We, in this, early study, we did show that it would have been more than 3 watts for this 16 element, 16 user array. And then this really constitutes, so, what does this really mean? It's more than 50% of the power dissipation of the entire 16 element front end. So if I was to calculate the power for all of these RF transceivers, the total power, the power in this I/O over here would be more than 50% of that total. So it's huge. And so we really do need to cut this down. And then, like I said, if we're going to increase to, say, a much more reasonable number of elements for 6G, which we're expecting to do, that interface power grows to over 20 watts. And we really cannot afford this. If we use EMIB to integrate the parts, we can see a 6x drop in the I/O power. And even using a macro 3D stacking technology, such as Foveros, we can already see an approximately 13x decrease in I/O power. So significantly compelling to use, multi-die heterogeneous integration for these systems. So now what I'm going to end with is a quick review of where we're at with enabling sort of the 3D chiplet ecosystem in the future. We do need an open source SPI. And just like AIB 1.0 and 2.0 paved the way for innovation in 2.5D, I think an open source 3D PHY will also pave the innovation on 3D chiplet integration and create a 3D chiplet ecosystem. This AIB and AIB 2.0 have paved the path for UCIe, which is now accepted by a consortium of companies. And so everybody can now design to one standard, and everybody can use each other's chiplets and integrate them into their systems, right? And that's what we want. And we've seen this already, where Intel's been collaborating with many different, academia partners and industry partners, and we've been able to integrate their chips into our FPGA ecosystem. We would like to do the same for AIB 3D. And so I hope you can, have a look at the specification and give us your feedback and your inputs, because really it's very early on, and it's just a version 0.5 spec right now. So in conclusion, we are in a sort of an era, entering an era where we're seeing intelligence, compute, and communication converge. And we do rely on heterogeneity to enable increased functional density, and especially for FPGA systems where this is absolutely necessary now in order to grow market share. If you're an FPGA company, you really want to do this. And FPGAs are really good at providing programmability at low latency. So if you want to create a system that has configurability, programmability, and you don't want to, take on the latency of a CPU, then definitely, have an accelerator hooked up to an FPGA, and you get this, really enhanced system that you can use for your application. There's a lot of innovations happening in the 2.5D and 3D packaging and area, but now the package is the system. So we all have to learn about what packaging is. We all have to learn about what goes into packaging, and we have to see this as a tool to enhance our platforms. Standardization is absolutely important. In order to have a healthy ecosystem, you want to have a single pipe that you can use to build all your different pieces. And then really, I would see that, wireless and 6G are really the drivers of this, these technologies where, they have been the early users of these technologies in the past, and I see that they will continue to be so in the future. So we are entering this new dimension of Moore's Law with these chiplet-based architectures, and I hope, you will be joining that journey with us. And, as I want to end with, a quote from our co-founder, don't be encumbered by history, go off and do something wonderful. Thank you.
Thank you very much, Farhana. That was very, very nice presentation indeed. That's a good quote as well, right? That's a good quote for sure. I would say that it was a wonderful, wonderful presentation. And well, myself, I'm sure other people on the audience also would like to go to GitHub directly and start looking at the SHIP Alliance, and go back to the presentation that you had here with so many interesting references, and well, a lot to work to start understanding a little bit of that, right?
Yeah. So yeah, so in my presentation, I do list a lot of references, so you can.
That's really, really good. That's really good. Well, I don't think we will have access to the presentation after, right?
I can send you a PDF.
Okay. Well, mainly, I would say that the presentation is very clear, and just to have a better information about the references itself, right? So that they can distribute to the people. Mm-hmm. Okay, so I have a couple of questions. We didn't see questions on the chat. So we are talking here about high powerful data transmission systems implemented in heterogeneous integration 3D 2.5D architectures, right? But if we want to look in low power, maybe low performance IoT systems, we have what are the difference that we should look? I know that the heating is very important, and
thermal,
yeah,
very important.
When you look at IoT, which is sensitive to temperature as well, because the systems are not so well dimensioned that as the power ones, right? And if you look at like clock information, and even the RF systems that can get very sensitive to the power consumption, right? So can you comment a little bit on that difference when you look into IoT systems, for instance?
Well, for IoT systems, IoT systems don't preclude you from leveraging some of these technologies because they're so tiny, especially hybrid bonding, where it's like less than 10 microns for the bump pitch. Not even bumps; they're kind of more like little nano TSVs and VIAs. So, I would say that as you scale the bump pitch on these 3D heterogeneous integration systems, it becomes like monolithic integration. To be honest with you, you're kind of like designing in a monolithic way. And so I think IoT systems could benefit from it in the sense that you could bring the analog mixed signal closer to the digital, and improve your power performance that way as well. So anything that you might think of putting, in
Okay.
sort of tiny little pieces and integrating them separately, you may want to fuse them.
Mm-hmm. Okay. I have one question here at the chat from Paulo César Comaceto de Aguirre. Thank you very much for the nice presentation. Can you comment on about the main challenges regarding the IOs itself? What is the maximum sampling data rate that we are achieving? I think you showed some of that in the presentation.
We did.
Right?
So we're shoreline, terabits per second with AIB 2.0. So over a terabits per second for like per millimeter shoreline, right? So that's quite big.
I have another question.
I have
regarding the simulations here. Now we probably another question here is about the simulation environments.
The simulation environments.
I mean the simulation domains. Let's say like temperature and mechanical.
Yeah. So modeling basically. Yeah. The modeling. So I mean, you would have to get obviously models for all of these. So whoever you're working with in terms of the packaging and integration technologies, they would have models for this, and so you would be able to simulate across the interface, right? So yes, the good thing about AIB way of doing things is that it really is agnostic to whatever you're using, and so really, because it's a source synchronous system, you know that your data and your clock are going to be aligned if you implement the AIB correctly, for example. So whatever losses you have through the package, you can recover in terms of phase. But definitely for reliability and everything else, you probably do want to have a good model for the packaging technology. I actually am late for another meeting, so I will have to stop it here.
Yeah, no, thank you very much for your presentation. It was really a pleasure to have you here and to see what is going on here in terms of heterogeneous integration, right? This is for sure something that we need to look at because it's coming right away. Right? Thank you very much.
And I'm happy to answer questions over email. So if anybody didn't get their question answered, I'm happy to address it over email.
Okay, so thank you very much. I would like to thank you again, and on behalf of the chapter, South chapter of IEEE, SCS, and EDS, we thank you very much.
Thank you for having me. It's an honor. Thank you. Thank you.
Thank you.